Today we're looking a little bit more at sequences in a lesson called Home on the Range. So today's objective is, given a decreasing sequence, we haven't looked at those yet, I can correctly choose arithmetic or geometric and calculate the common difference or common ratio. So those are some vocabulary terms we've covered already. Remind yourself what those are. We're looking to get 2 out of 2 problems here. So here are some things to think about. When does an arithmetic sequence decrease? What makes that happen? How can a geometric sequence be decreasing? Think about the pattern that geometric sequences have. How would that decrease? How are equations of decreasing sequences different than those of increasing sequences? Okay, so first a quick review. Tell me everything you know about arithmetic sequences. You might want to pause the video and think about this on your own, see if you can come up with some answers. The really obvious one we get right away usually is we add or subtract at each step. But there are other things we know as well, so maybe pause the video and think. Think if you can come up with anything else we know about arithmetic sequences, and then I will show you some. So we also know that arithmetic sequences have a term called a common difference. This is the number that is added at each step. We also know that we use this function to model an arithmetic sequence, where m is the common difference. And do you remember what b was? B was the value at step 0. We might also call this the first value. Then we could also do graphs. If we wanted to graph this, what would it look like? We'll choose a different color here. What would a graph of an arithmetic sequence look like? Well, since we're using the mx plus b, that slope-intercept form, it would look like a line. So we know that arithmetic sequences form lines, and the common difference we discovered was the slope, and the value at step 0 was the y-intercept. So we know all of these things about arithmetic sequences. Awesome. Okay, so now tell me everything you know about geometric sequences. Maybe we can remember some similar things. Once again, the most obvious thing is multiply or divide at each step. What else do we know though? Maybe pause the video and think about, maybe can you name some things about geometric sequences? Maybe what a formula looks like that we would use. Maybe what the graph looks like. So the function we use for geometric sequences is a times b to the x. And you'll recall that a is the value at step 0. Or we can call that the first value. And b, do you remember what b was? It's the common ratio. Kind of like the common difference, it's the number we're multiplying at each step. So common meaning at each step. And then if we wanted to graph this, what would it look like? So this usually starts somewhere down here and then grows really rapidly, something like that. So it's not a straight line for geometric sequences. This is called an exponential. So we might write that as well. This is exponential. Exponential growth. Sweet. All right. So can you remember when we write an equation, we need 2 things. We actually just talked about them in the last couple of slides. Do you remember what they are? 2 things to write an equation for any arithmetic or geometric sequence. What do we need? Well, the first thing we need is the common either difference or ratio, depending on the type of sequence. And then what's the other thing we need? We need the value at step 0. So once we have those two pieces of information, we can use the general form of the equation and write the equation for the sequence. So this just summarizes that common difference and common ratio. Common difference is the number you add at each step. The common ratio is the number you multiply at each step. And then this slide is a summary of everything we know about making an equation from a sequence. Now this is a really busy slide, but it's really just putting together information we've already covered that's probably already in your notes. This would be a really good one to take a picture of. Just pause the video and take a picture of this to put in your notes. You can see this is the linear form for arithmetic sequences. This is the exponential form for geometric sequences. And today we are going to tell a story about prairie dogs. Sad, sad prairie dogs. So prairie dogs are small mammals that are members of the squirrel family. They average about 14 to 17 inches and live in underground colonies called prairie dog towns. They're native to the Great Plains region of the United States. So there's a little prairie dog right there. Cute little guy. But the prairie dog population is estimated to have declined by 95% over the past 200 years. So prairie dogs are dying out. Super sad. To protect the prairie dogs, people have set up Prairie Dog Reserves, which are places where the animals can live happily away from human activities that threaten them. Look at that. They're so happy. They're just a little dancing around. One Prairie Dog Reserve was established on 120 acres of land in 2015. But as the land has become more valuable for humans, people have reduced the size of the reserve. Shocking. This prairie dog is very shocked by that fact. Very shocked. The following table shows the size of the reserve over time. All right, well, this is where we get to the math stuff. We're looking at the size of this reserve over time. So you can see in year 1 it started at 120 acres, but at year 2 it dropped to 112.5. Year 3 to 105, and so on. It kept dropping every single year for 5 years. And it asks, does this sequence show a common difference, a common ratio, or neither? How can we determine that? Let's think on that. Well, if it's going to be a common difference, then we'll either be adding or subtracting the same number. So let's try that. What do we need to subtract here to get 112.5? How would you figure that out? So I'm going to do that. I'm going to just subtract one from the other. I'm going to do 120 minus 112.5, and I get 7.5. So I must need to subtract 7.5 in between here. So let's see if I subtract 7.5 again, if I get the next number. Subtract 7.5 from 112.5, and I get 105. Yeah, that did work. Let's see if it continues again. Subtract 7.5 again, and I get 97.5. Yep, that is our pattern. We are subtracting 7.5 every year. So this sequence is showing us a common difference. And what type of sequence? Well, since it's a common difference, this is going to be arithmetic. And then it says to write an equation to model the size of the reserve over time. Okay, so we need to remember what equation we use. We can go back and look at our notes. In fact, here's a handy thing, might help us. Arithmetic, we determine this is, we're subtracting arithmetic. That's the form we're going to use with these values. Common difference and the value of step 0. Okay, let's go back up here and write those. We're going to use f of x equals mx plus b, where m is the common difference. Actually, I'm not even going to write that. We're just going to write the number. What is the common difference here? M is what? M is negative 7.5. And then B is our first value, or it can be our value at step 0. So depends on how we set this up. We could say step 0 is up here, or we could even say year 1 was step 0. It actually doesn't matter too much. But let's just say step 0 is 1 back, just for a moment. All we'd have to do to find step 0 is we'd have to add 7.5 to get the previous term. So this would be 127.5 for step 0. 127.5. So now we just plug those in. F of x equals negative 7.5 plus, negative 7.5x plus 127.5. There we go. That's our equation. So that follows the form mx plus b, where m is our common difference and b is our value at step 0. So continuing on with our story, when the reserve began, there were about 600 prairie dogs. But biologists found that due to disappearing habitat and other factors, the prairie dog population has been declining at the reserve at an alarming rate of 20% per year. Wow, so the population has been going down really fast. Let's do a quick review of percentages, or maybe you haven't seen them before and that's okay too. Let's just remind ourselves what percentages mean. When we see a percentage sign, that means we need to move the decimal place 2 to the left and then multiply. So our decimal place is right there now. We're going to move it 1 and then 2. And we wind up with 0.20. And then we multiply by the 600 prairie dogs. 0.20 times 600, I'll put that in my calculator. I get 120. So that's how many prairie dogs are being lost each year. That's how much the population is going down. Not each year, but at least the first year. It's going down 20% each year. So the starting population was 600. We're trying to figure out what the ending population was every year. We lost 20% the first year. We said to calculate that is 0.20 times the beginning population, which we got as 120. So to find the ending population, we just need to subtract this value from the original starting population. 600 minus 120, oops, not 128, 120 equals 480. So then our starting population was our ending population the previous year. We do the same pattern. We multiply by 0.20 times 480. And what do we get there? Put that in my calculator. And I get 96. So our ending population is going to be 480 minus 96 equals 384. So pause the video here and see if you can fill out the rest of the table before I do, and then compare your answers and see if we get the same answer. So then our next starting population is 384. We do 0.20 times 384. We get 76.8. Now, I don't know what 0.8 prairie dog is, so I'm just going to round that to 77 because we're talking about whole prairie dogs here. So now to get the ending population, I take the beginning minus the number lost, and we get 384 minus 77 is 307. Let's do one more iteration. We start with 307. 0.20 times 307 equals 61.4, so I'm just going to round that down to 61. And then find the ending population. We get 307 minus 61. And so my last population for that fourth year is 246. So these ending populations are what we're going to track. We're going to look at how the population is changing each year. And the question is, does this describe a common difference, a common ratio, or neither? How are these changing? How can we tell? Well, our first attempt is usually to see if it's a common difference. Let's see if we're subtracting the same amount each time, because it is going down. So this would be minus 120. I again can tell that because if I just go 600 minus 480, I get 120. So that's how much the difference is. Let's see, if I subtract 120 again, oh, I should actually get 360, not 384. That's wrong. That didn't work. If I subtract 120 again, this should be 284. Yeah, that's not working at all. This one must not be an arithmetic sequence. What about a geometric sequence, though? Is this possibly a geometric sequence? How would we be able to tell? Well, basically, we'd have to figure out, is there something we're multiplying by here to get 480? How would we know what to multiply to get 480? Well, maybe we could set it up like this. 600 times something equals 480. Oh, well, this looks a little bit like algebra, doesn't it? If we just replace that question mark with, good old variable x, we can divide both sides by 600 and we get x equals 480 over 600. If I put that in my calculator, I get 0.8. So we're thinking maybe if we multiply by 0.8, maybe we'll get these numbers. Let's see if it works. So multiply 600 by 0.8, put it in your calculator, see what you get. 600 times 0.8 is 480. That worked. Let's try it again. Multiply by 0.8. 384, that did work. Let's do it again. 0.8. 307, yep, and one more time. This looks like our pattern. We found it. 246 when we round. Yes, that is correct. So we found this has a common ratio. And the common ratio has a value. We're multiplying by 0.8 at each step. What type of sequence? Well, since it's a common ratio, this is going to be geometric. And then we need to write an equation to model the population over time. Okay, let's go remind ourselves of what this looks like for geometric. Here we go. Geometric sequence is going to use a times b to the x. And then a is the value at step 0 and b is the common ratio. Okay, so let's come back down here and write that. This is going to be f of x equals a times b to the x. And a is going to be the first value at step 0. Oh, once again, I'm not going to write it. I just want to write the number. This is the value at step 0. It's right there, 600. A is 600. And b is the common ratio, which we determined was 0.8. So our overall function here is going to be 600 times 0.8 to the x. Now notice something about this sequence, this geometric sequence. It is going down, right? 600, 480, 384. It's a decreasing sequence. But our common ratio is not negative. Now it made sense with the arithmetic that it be negative, right? Because we're just like subtracting each time, so that would go down. But in a geometric sequence, for it to go down, it doesn't need to be negative. There's something else going on here. It's not negative. What's What's different about this number than the ones we've looked at before? You may have noticed this one has a decimal. So a number less than 1, if that is our common ratio, if it's less than 1, that's what's going to make it go down. So if our common ratio is less than 1, then the sequence is decreasing. And that's specifically for geometric sequences. We look at the common ratio and see if it's greater than 1 or less than 1. Cool, so we looked at a decreasing sequence for arithmetic and a decreasing sequence for geometric, and that covers today's objective. Given a decreasing sequence, I can correctly choose arithmetic or geometric and calculate the common difference or common ratio. The common difference is going to be negative, and the common ratio is going to be less than 1 but greater than 0.